Let's go. Okay, so my plan for today is to, so today and tomorrow morning, okay, for me are one unique entity. So it's not that you sleep.
Keep going speaking until tomorrow morning.
Exactly. Please bring me something to eat from the restaurant, and I'm fine. Can sleep here, no problem. So the things that I want to cover, which remain, are the beta lattice Anderson model, an exact solution, at least for the localization and the transition. The transition in general, and in particular RG, the RG flow, which is generated by the Anderson transition, as it evolves from one to infinite dimension. And this will be based on a modern interpretation of the Gang of Four paper, which allows us to go to infinite dimension and hypothesize the form, the topology of the flow of two-parameter scaling. Okay, so to tell you, for example, two-parameter scaling is very different. It's Kosterlitz-Thouless. One-parameter scaling is easing in 2D. Okay, 3D. Okay, so since the Anderson model does not have an upper critical dimension, we have a different flow for every dimension. Okay, all the way to infinity. At infinity, we have a new universality class. And our claim in the recent papers with Boris Altshuler, Volodya Kravtsov, Piotr, and Carlo Vanoni, our claim is that universality class is two-parameter scaling, very similar to Kosterlitz-Thouless, not identical, very similar to Kosterlitz-Thouless, and that is also relevant for understanding the numerics of MBL. Okay. And then the other thing that I wanted to do, and for this I will use hybrid blackboard and projector, but this certainly will not happen today, is to discuss Basco and Altshuler's paper in terms of diagrams, approximations that they make, and how to make approximation you have to make to go back to something which is like this. Okay? Very good. Right. So let's start. Yesterday we had the problem. The problem was that on a lattice, we wanted to compute in the simplest approximation, okay, the sum over paths here, okay, to see if actually the amplitude, the propagator to go from one point to the other was actually exponentially decreasing. We found that the number of paths is approximately exponential, okay. And therefore, the random numbers, okay, the propagator, we wrote it as a sum over paths p from x0 to x of the product of the sites of the paths of these things. Too many x, I, okay. But these are not IAD random variable. They're not independent. Okay, they're identical distributed, but not independent. Okay, so we said, well, there is actually, so we did an approximation, which is independent, and then we found an analytic result. Then I gave you a numerical scheme that you could use to actually compute this thing, irrespective of the fact that the paths themselves are independent. Okay, and this is transfer matrix of Medina and Kardar. Okay, and then I said, well, there is another problem in which actually there are an exponential number of paths which are independent, and this is the beta lattice. Beta lattice or Cayley-3 is something like this. Okay, it's a great lattice to do statistical mechanics for two reasons, which are obviously connected. The first one, for example, spin glasses, people use this all the time, okay? In fact, the approximation in which you take any lattice and consider it as this thing is called belief propagation. Okay, and now it's all the rage in numerical methods. Okay, you have a lattice. You want to understand. You have some sort of equations that you have to solve, typically linear equations, and you want to solve this by some approximation. This approximation is essentially thinking of the lattice. One of the approximations that do is called belief propagation, BP. Okay, is to approximate your lattice with the Cayley tree. Okay, very good. So you can do so the two things is exactly solvable by recursion, and whatever the upper critical dimension of the underlying model is, this thing is above. Okay, so it's infinite dimension now.
Okay, because it is infinite dimension.
Yes. So whatever model you put on this thing is going to give you the mean field behavior. Okay, you put the Ising model, you put the spin glass, you can put the Potts model, you can put XY. People are still working on this thing to these days. For example, the continuous spin glasses, for example, spin glasses with the clock instead of a plus or minus one. They still unsolved, even on the Weta lattice. But the good thing about this thing, as I was saying, so if you take one point, your x0, and you look over x, there is a single path, okay? And then what you have to ask for is, among all the points at a given distance, of which there are exponentially many. Okay, so let's define K is the branching of the lattice. In this case, the branching is 2. And the connectivity is K plus 1, which in this case is 3. Okay? Now, the number of points at the distance R from x0 is K plus 1 times K to the R minus 1. Okay, which, let me rewrite as K plus 1 divided by K times K to the R, which in this lecture will be K to the R. Okay? Very good. So, and to each of these points, there is a unique path that goes there. So if I want to look at the maximum probability, I don't sum amplitude because these are different points, okay? The maximum probability to find, sorry, the total probability of finding my particle put in x0 at distance x, at distance r, okay? I have to maximize over k to the r. Now they are IAD numbers, and I'm fine. So the calculation that I did yesterday is correct. It's still approximate because I forgot. I remember I removed the self-energy from here, okay? But there is another way to solve this thing, and the thing is the following. Take half of, take this lattice, okay? Okay, this is gone. Take build the lattice like this. Suppose I have two pieces very large of 3, okay? Cut at a certain point. And then I add the site. So this is site number 1, this is site number 2, this is site number 0. And I connect it now, okay? What did I get? Exactly the same thing, okay? So now, suppose I know G11, okay? Which is in absence of this object. Actually, let me use a different color so that G11, okay? Which is the propagator to go from 1 to 1 in absence of the red lines. Okay? G to 2, which is the propagator to go from 2 to 2 in absence of the red lines. Okay, what I'm saying is that this is 1 over E minus H, let's call it 0, I don't know. Okay, the one in which I've removed the 0 site here, okay? And then 2 is the same thing. Now, the probability per G00 is 1 divided by E minus E0, which is, again, the propagator in absence of the other two things. And then you have to add the self-energy. Okay? The self-energy, since 1 and 2 are not connected, if not by 0, it's simply hopping T, okay? It's simply T square G11, T square G22, okay? And as you see, I now have a recursion equation. If I know 1 and 2, I get 0. Now I take another branch, I merge it to 0 and 0 prime, and I want to add another point, and so on and so forth, okay? So let me remove the repetition, 0, 0, 0, okay? So these are called cavity propagators. Why cavity? Because this name is taken from spin glasses, actually. So this cavity propagator, because these are not really the propagator of a site with 3 connections. They are propagator of a site with 2 connections. But again, if I want the propagator of a site inside the beta lattice, I just need to merge 3 of them. Okay? So let me study this, and then I really want G of I, where I is now inside here, I take 3 of these and I do the same trick. E minus EI minus sum T squared, sum over J that goes from 1 to K plus 1 of GJJ. Instead, these ones, now let me remove one of the indices. Let me call them G0 small, epsilon 0 minus T square sum for J that goes from 1 to K of Gj. Okay? So once I know this, I know this. Okay? Now, if epsilon or T are random variables, these are random variables. So every time I do this thing, I get a new random number. And I keep doing, and I get a new random number. How do I know that I've reached convergence?
Sorry, before going there, just to be now with the new notation, you agree, just to be sure that
Yes.
I'm on track. You agree that this big G00 is now a bit inconsistent. Because in GII, the full propagation.
Yeah. Sorry. Okay. Yes. Yeah, I was using the different indices. Because this is this. You realize as soon as you find that this is K plus 1.
Now you put the cavity propagator with small g.
Yes. So I want convergence in this equation. Once I have the convergence in this equation, then I will find this thing. How do I know that I have convergence? These are random numbers. What converges about a random number? What defines a random number? The probability distribution. Okay? So I have a probability distribution for the G at the given steps. Then I go down and I get another probability distribution. Then I go down and get another probability distribution of, in general, complex variables, because here I can add an imaginary part. Okay? So this probability distribution evolves when I keep merging until it reaches a certain stable distribution. Once I reach the stable distribution, it's my thermodynamic limit distribution. I get that, I extract k plus one of these things, and I create a new probability distribution, and that's everything I need for. Okay, it's the probability distribution of the cavity fields. Now, if you want the probability distribution of this thing, you can write, if you want to write down PG will be expectation value and disorder, okay? So epsilon 0, the expectation value over the G's, okay? PG1, PGK of delta function of G minus this thing. Okay? So if you don't like random variables, simply you need to solve a nonlinear integral equation. Okay? We have a nonlinear integral equation for functions of complex variables, and I need to solve it. Numerically, it's a mess.
You're doing at the end an extra integral over zero.
Yes, I'm taking the expectation value of the epsilon 0 of this thing. Okay? But there is a quick, dirty way of doing this, which is called population dynamics. Okay? And by the way, this was all invented in Abu Chakra, Anderson, Towles, 1973. Okay? Including the numerical method. The numerical method is the following thing, which has been rediscovered many times, also in the context of spin glasses and so on and so forth. So the numerical method is the following thing. Go in your computer and create an array, a random array, okay? Take a population size, large, 10 to the 6, okay? And make an array of G1, Gn pop, and complex numbers. Then, step 2, pick 2 of them random. Let's say pick 3 of them random. GA1, GAK, merge them. Merging means compute this into a new one, G new. 3, replace element, population, G new. 4, until convergence.
Repeat it only from the item 2, right? You do not repeat item 2.
Yeah. The initialization is this. Okay. Now, repeat until convergence. You have to be careful here because, as I explained yesterday, this probability distribution typically don't have a mean. Okay. So you don't want to use the mean or variance, God forbid, they all diverge for convergence. Okay. You have to look at some other things.
So practice when you run it in a computer, what you keep doing until they don't change anymore too much, or
Yeah, the histogram doesn't change much. some Kullback-Leibler, for example. If you add the imaginary part here, with the imaginary part you reach convergence. There is, then you need to take the limit when the imaginary part goes to 0, and then it becomes problematic, okay? But if E has an imaginary part, then it will converge, will always converge, and you will realize whether the distributions are long-tailed, so localized, or not, when you send the imaginary part to 0. Okay?
Easy. Practice fast the convergence or slow?
And so far, if you are close to the critical point, no. That's the point. I mean, you have critical slowing down of this algorithm as well. This is a kind of Monte Carlo too. Close to the transition, you have critical slowing down.
Or even where the critical point is entering only by one number, epsilon 0, essentially, because all the rest are
the width of the distribution. Yeah, here. This is,
Yes.
integral in d epsilon 0 of epsilon 0, blah, blah, blah. Sorry, you also need to pick a random pick. I forgot, yes. I mean, it was in the merging. It was in the merging procedure, but you have to pick a random epsilon 0 with a set bit probability.
The epsilon 0 is in the initialization, right? You extract once for all, or
No. Every time you compute a new, you have a random. Because you are adding a site.
Different sites are
different sites have different energies.
Okay.
Okay. Good. Very good. Now, so we cannot solve this in general for we cannot solve this in general for when you have the disorder. One thing you should check is that actually this has the correct fixed point if I don't have any disorder. So for example, if I don't have any disorder, I just have the adjacency matrix on the graph. So all the sites are equal. So I have 1 over E minus E0 is 0 minus T square KG. Okay? Let me solve this. This gives me G equal to E plus or minus square root of E square minus 4 T square K divided by 2 T square K. Okay? I plug it in here. Also, this one doesn't have any disorder. G is 1 divided by E minus T square K plus 1 times G. Okay? And I need you to do the calculation. Okay? And now you can, for example, take the imaginary part of G, E, okay, plus I0, for example, divided by pi. And this is the local density of state, rho E. And you will see that this, for example, for K equal 2, has this form. Okay, and goes between minus 2t square root of k and plus 2t square root of k. Another exercise for you. The square root comes from the imaginary part comes from the square root. Another exercise you can do is take this thing, scale t as tau divided by square root of k, take k to infinity, and you will find Wigner semicircle. Okay?
About the other limit, because let's say in the limit, like k equal to 1, I should get plane waves.
You get
Because then
yes.
zero disorder, so I go to the plane
I think
waves.
so. I think so. In fact, the minus 2t and t, yes. Yeah, you get I think you get,
K equal to 1 is 1t.
yes.
Exactly, that's why.
You get,
Yeah.
yeah, you should get
So
plane
it
wave,
does get-
which
Yeah, the plane wave.
has this thing, right?
Okay.
Yes. Yes, diverge there, yes.
Mm-hmm.
A k is larger than 1, you don't have divergence, it goes down. So it becomes to be similar to random matrix. And when you send k to infinity, it becomes a fully connected system, and we know it's random matrix. Correct. So we get Wigner semicircle. Okay, good. Now, I remember the question until this point. Okay, fine, fantastic. Either everybody's asleep or everybody understood everything. You know, the curve of questions as a function of understanding number of questions. It does like this. You're not sure if around here or around here. It's a non-invertible function, so okay. Okay, good. Maybe good. I don't know. So, what was I saying? Yes. Okay. So now we have these probability distributions. In principle, assume we can solve in some way this integral equation. And we have this P of G, okay, which it's actually a function of two things: P real part of G, P imaginary part of G, okay? And if we take the marginal and we look at P of the imaginary part of G, this is P of I, okay, density of state, local density of state. And if you believe what I told you, is that you can distinguish the localized from the delocalized phase, whether the imaginary part has a variance or not. Okay? So if you take your probability distribution, okay, and then you do it with, you know, n pop 10 to the 5, 10 to the 6, 10 to the 7, okay, as the number, the size of the population increases, this probability distribution shrinks to a delta function. This delta function is centered around rho v. So for example, if you add a little bit of disorder here, okay, then you run this thing, it will converge to a probability distribution picked a particular value of the imaginary part of the propagator, so on the local density of state, which will resemble a little bit like this. It will actually change, you know, but this variance will go to zero when we send the population size to infinity. Instead, so this is if W is less than W critical. Instead, if W is larger than W critical, okay, then this probability distribution, sorry, will be very typically one looks in log scale, log P, log imaginary G, and this will look something like this. Okay, so you need to do two things. First, send n p to infinity, And second, send the imaginary part of V to 0. When you do this,
shouldn't I have a pure point for the localized space? Should my density be a pure point?
a given site. This is a distribution. So you are summing over all the sites.
So this is not the local density of state. This is the total density of state.
The imaginary part is the local density of state at a given point.
Okay.
The problem is when you have pure point, this means that when you change the energy in the same ensemble,
Yeah.
okay, this does something like this. Okay, so there is the integrated local density of state does this.
Yeah.
It's not the same thing. You are looking at a function of the energy. Here we fix the energy and we look at all the points. Okay, so this is the probability distribution of this value at fixed energy, okay, taken over all the points. It's random because this David staircase is random.
So in other words,
Okay. Now you can study the okay, now good. So this in principle, if you know this, you know everything. Okay. I'm not touching on other methods of solving this problem, which essentially reduce also to iteration equation. In particular, the method of supersymmetric, the supersymmetric method, which was pioneered by Zirnbauer, who solved this problem using the supersymmetric method in the middle 80s. Okay, that allows also to have some understanding, analytical understanding of what's going on, both in the localized and delocalized phase. Okay. It's not percent sure to me if you get really much more than if you were able to, if you actually analyze this thing properly. However, there is a very recent paper in which a lot of these numerics is put together also with the results of the supersymmetric method just for the localized phase. And it's a nice little paper by, by Marco Tarzia. Who's the other guy? It's the guy from CNR in Rome. No, Roma, Tommaso Rizzo. Rizzo, I think it's either 24 or 25, actually. It's pretty recent. Tarzia Rizzo, in which they analyze this thing very precisely with, you know, a more refined version of this thing, but still this thing. And they compare it to, they find also the participation ratios. I think it's a very nice little paper, very easy to read. I strongly advise you to go and look at it. Okay, very good. Now, susceptibility. Okay, good. Now, suppose we have this thing, okay? And we want to look, so if I look at the probability distribution, okay, it's in particular close to the transition is going to be difficult to distinguish whether this thing actually has a width, finite width or not. Why? because close to the transition, there is critical slowing down. Okay, the population cannot decide whether it's on one side of the transition or the other. Okay, so essentially it's really slow. You change the population size by orders of magnitude, 5, 6, 7, 8 orders of magnitude. And you see only a little shrinking, okay? So it would be great if we could actually define and calculate the susceptibility. Susceptibilities diverge at the transitions, you know, right? Okay. Well, there is an easy way actually to define susceptibility here. If you think about the physics, okay? If I have a localized state, and I change the energy on one site, and then I look at the site very far away, would this do anything? So, for example, I have a localized phase, okay? I change the energy of this object here. This has, let me call it 3. This has energy epsilon 3. I change it by epsilon 3 goes to epsilon 3 plus delta epsilon, very small. And then I look far away at site 0. Will the propagator 0, 0 be affected by this change? No. The wave functions are localized. If this distance is larger than the localization length, we don't care, right? Okay. So let me do exactly that. Let me take, first of all, let me straighten out this beta lattice. Okay. Let's look at the only part that goes from my initial site, let's say site 1, okay, to my last site, let me call it site L. Okay. There is only one path. Then there are other things that get into. Okay. There are k minus 2 other lines that get into this thing here. So I have k minus 2 plus 1 is k. Okay, so I've just rewritten my beta lattice like that. Okay, in fact, if k is equal to 2, sorry, it's k minus 1 actually, because the connectivity is k plus 1, so minus 1. In fact, if k is equal to 1 and we have a line, we don't have any of these things. Okay, good. And then I take my g I take the derivative with respect to epsilon 1. Now, I use a telescopic identity, GL minus 1, dGL minus 1 divided by d epsilon equals blah, 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 and I expand this. But then you realize very easily that dGL by dGL minus 1, since G, see, here I have G, okay, so this is L minus, GL is 1 divided by E minus epsilon 0 minus GL minus 1, okay, this one, here times T square, minus T square sum of J that goes from 1 to K minus 1, GK, okay, GJ, Actually, let me call it G tilde because the G's are the one on this part, and this one, actually, let me even color them. So unless you are color blind, this should make it clear. GJ, okay? The derivative dg by dgl is just gl squared because gl minus 1 is in the denominator, okay? So this susceptibility is gl squared, gl minus 1 squared, blah, 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 g2 squared, and then I have something dg1 by the epsilon. Okay? So I have g squares times something of order 1, which I don't care about, okay? So this is the product over I equal 1 to L minus 1, doesn't really matter, of GL squared, GI squared. So formally, I have this product here.
We also T squared in front of.
There should be T squared. Yeah. There should be also T squared because every time I take a derivative, I bring T squared. So there are prefactors here that are important. So let me set T to 1 for the following, okay? So this susceptibility will be a random number, that doesn't have an average, because we know that whenever we take averages of this thing, we get infinity. And this, if we analyze this susceptibility, we need to ask ourselves whether the typical value of the susceptibility, okay? So the probability that the susceptibility is exponentially small is 1 or not. Okay, so if this now decays, if chi now decays exponentially, then I am in the localized phase. If chi diverges exponentially, we are in the delocalized phase. Notice, okay, stop here. Notice one thing. Typically, the susceptibility in phase transitions diverges at the phase transition, doesn't diverge on the other side. The only counterexample to this that I know, if you look at nonlinear susceptibility, is spin glasses. In spin glasses, the susceptibility diverges at the transition and stays infinite in the entire phase. It's the same thing here. Why is it exponentially large in the delocalized phase? Because if I have plane waves, okay, and I change the energy, then my plane wave will change. Okay, it's like this is you can see at this kind of divergence. So the structure of the plane wave will not change much. Okay, the phases will change a lot. So if I look at just the propagator with all the phases and everything, this is going to change a lot. Okay, so that's the important thing. If you look at other things, for example, the imaginary part of the propagator alone, then we know that that doesn't change, right? That's in the delocalized phase, we say that that's a delta function, so there is no susceptibility for that. Okay, but if I look at this, this will diverge. So the point at which there is a divergence, that's the point at which there is the Anderson transition. Okay, good. Now, very good. How do we find? So everything I'm going to tell you now, you can find in various forms in various papers. The one which I'm going to talk about is the following paper I wrote with Valentina Ross, Giorgio Parisi, Francesca, Pietro Caprina, Saverio Pascazio, and myself. Okay, very good. So, again, I have this random variable chi that tells me if I change the energy on one side at a given distance L, what happens at distance L? Okay, and now, obviously, what I have to ask to stay in the localized phase is that if I do this on all possible sides at distance L from my final point, this is true. So again, I have to look at k to the L of these random variables here, which have a certain probability distribution, let me call it Q, QL, and then I have to ask that QL, k to the L, is equal to 1 to see the transition. Okay. Let's find QK. Okay. We have to find QK. First of all, let me take the expectation value of KDS, okay, with S less than 1/2. Why S less than 1/2? Because if I take S less than 1/2, I take G to power less than 1, and therefore the averages exist. This method is used to make, actually, to turn these calculations into a proof. In fact, it's called the fractional moment methods, and it is what Michael Eisenman has used with Simon Warzel, also before, actually. Warzel, Robert Sims, and other people. 2010, 10-ish, okay, to prove to solve analytically, mathematically, prove the transition.
What about QL? This probability?
The distribution of chi.
Oh, okay, okay.
Yeah, and there is an L because I'm defined it by as. Okay?
Yeah, but you want to see the prediction of pi in all these L sites.
I want to see the probability. This is a random variable. Okay? So I want to see the probability distribution of this random variable. Then I have KL of them. But I want to see probability distribution of one variable, where IAD. Okay? Good. Very good. Okay. So, why is this important? Because if let me write this explicitly. This is Q of chi to the S. Okay? Let me assume that this thing, based on this, is some function, small, not exponential, which depends on L, okay? Some number, lambda S, to the L. And this is an assumption. Now we're going to see this is true. But yeah.
You're assuming that chi is positive.
It is, it's product of squares.
Oh, because it's squares and you're
Yeah.
not taking.
Yeah, I'm not taking the last thing.
No, the imaginary parts are 0.
Yeah. We're taking imaginary part to 0. Yes. You can see this also as a susceptibility towards turning on an imaginary part. You will get exactly the same thing. If you turn on an imaginary part, I told you I was changing the energy epsilon 1, I didn't tell you if a change was real or complex. Okay, it's the same thing. If you turn on, add a little imaginary part here, if this imaginary part dies, then you are in the localized phase. If the imaginary part creates a scramble, okay, then you are not. Okay, good. So let's assume this is the case. Then I can invert this function here, right? I can invert because this is a Mellin transform. And I get the Q of chi is integrand ds divided by 2 pi I over the Bromwich part chi to the minus s minus 1 Cn lambda of s to the L. Okay? And if I write lambda of s e to the mu s just for fun, and theta as log chi divided by L, this is the analog of the zeta we defined the other day. Okay, then this becomes CL integral in the S divided by 2 pi I over 1 which part e to the minus L S theta minus mu of S. Okay. And for L that goes to infinity, I can do saddle point integral here. So this integral is over, I have to look where the singularities are. Certainly there is a singularity at s equal 1/2. Okay, maybe there are also other singularities. Okay, and then I have to look at the form, the Bromwich path to pass. I forget about the singularity. I want to pass close by. I want to pass on the saddle point. Okay. Okay. Very good. The saddle point I will have that mu prime of s is equal to theta. Okay, and then I can invert and I find s star s star of theta, and then I will have that q of theta will be e to the minus L s star theta minus mu of s star. Now I want the maximum of this, okay? So I want to look at k L q of theta is equal to 1. You see that this goes into this thing here. Okay? So the equation will be that's the maximum will solve k e to the minus s star theta minus mu of s star is equal to 1. And now I remember one thing. So this will give me, given the value of this order, I will get what's the maximum value over k to the L of this thing. The transition is when this maximum value is theta, is chi of order 1, not exponentially small. Okay. If chi is of order 1, then theta is equal to 0. So at the transition, theta is equal to 0. So I have to look at mu prime of s star is equal to 0. Okay? At the transition. Mu prime s star is equal to 0. Then I have to multiply k times e to the mu s star, and this has to be equal to 1. And now something important. You can show that, and maybe I'll come to show, that there is a symmetry s that goes in 1 minus s. If there is this symmetry, the only mean, at least, if the function is continuous, the mean is to be at the symmetric point. And therefore, I know directly where, if I'm looking at the transition, I know directly that this is actually 1/2. So final step, let me rewrite this in terms of L. The transition point is when K times lambda to the 1 is equal to 1. Okay? Now, shall we make a short break? I can go on, maybe. Okay, let me go on for just to write down the integral equation, then we finish this thing. Okay, so very good. Why did they write that lambda? Because that's actually the eigenvalue of the integral operator.
It's smaller than 1/2, and now you're exactly at this point 1/2.
Sorry?
You mentioned earlier that S is smaller than 1/2, now
But
you're
now
exactly
you're-
at point 1/2. Okay.
Yes. Yeah, it's an analytic continuation. You define the function for S less than 1/2, then its Mellin transform is analytically continued to the S. Okay, and you realize because of the symmetry that the analytic continuation is symmetric in S that goes in 1 minus S, and therefore it must be the eigenvalue that I have to look at to see the transition is exactly S equal to 1. Okay. Now, these things here, they're not IID numbers, okay? Because one feeds into the other, feeds to the other, feeds into the other. This we need to take into account, okay? So when we do things like the average over GL to S, GL minus 1 to S, blah, 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 G1 to S, okay? This is equal to the integral in dg1, pg1, and that is the only thing which is independent here. But then we have the probability of G2 given G1, the probability of G3 given G2, and so on and so forth. Okay? Anti-negative probability of GL given GL minus 1. Then I have this GL to the 2s. Let me write here GL minus 1 to the 2s. Let me write here G3 to the 2s, G2 to the 2s. To the 2s, and here G1 to the 2s, okay? So if you see, this is the application of the kernel, this is the multiplication of the kernel K L times, and K Y X is the conditional probability of Y, say, one of these arguments here, okay, given X times Y to the 2s. Did I put it to the left or to the right? I put it to the right. X, the smallest one. X to the 2s. And this thing here is the expectation value over the disorder and the fields, the red fields, of delta of y minus 1 divided by e minus x minus t squared, the sum over the red fields, Still choice. Okay. So this product of correlated random variables is the expectation value of this product of correlated random variable is just the trace of this kernel to the L. So if I find this kernel depends on S, so let's put S, KS. So if I find the largest eigenvalue, I call it lambda, I obtain exactly this formula. Now, what do I need to find this thing here? I need the probability distribution of the fields, okay, because they feed into the red lines. The probability that I told you, you had to do the numerics to get the convergence and everything, okay? And then, you know, I have to compute this matrix, KS of YX of two real numbers. And then I have to look at the eigenvalues. You can actually do this. Numerically, it's not too much of a feat. And when you do it, you will find that you put 1 over k here as a function of s, and you look at lambda of s, and it does something like this. So I think it's easy to show that for s equals 0, this thing has, the eigenvalue has to be 1 because this is a probability distribution. Okay, so it's, you know, starts from here and then quickly drops down and then goes back here because of the symmetry. Okay. The symmetry was already recognized in Abu-Chakra and the Sutta. Then when we decrease the disorder, this thing actually starts moving up. And this here. And then at the critical point, this is what you get. Okay. At the critical point, you get that, then you get larger than that, and then in principle, you know. And yeah. So the solution, this equation here gives you the solution of the critical value. And in this way, you can estimate that the critical value is 18, for k equal to 18.12 plus or minus.
This is not the standard, like Abu Chakra didn't follow this approach, right? They followed
very similar approach. Very similar.
a self-consistent equation for the self-energies, and they look different.
It looks different, but it's not, because when you linearize, then you want to linearize that equation, right? Because you want to see if I put an imaginary part, do I develop the measure? So when you linearize, you end up with an integral equation, which is tantamount to this.
So what do you gain this approach with respect to the old approach, let's say, is
better computer.
Okay.
Yeah. Well, nothing. It's the same thing. It's the same. It's a dictionary between the two things. So it's not. And also in the supersymmetric.
Confused is that in the Abu Chakra they didn't do anything numerically. They just
They do. Absolutely. They do. They solve the integral equation numerically. They give some values which are wrong by 80%, but considering it was before I was born, I think it's a good, it's a great thing,
They solve it.
They do numeric. Yeah.
Okay.
They do various approximations and then they study numerically an integral equation, which is essentially this, just given in terms of this susceptibility, and they look at the linearization of the.
Okay.
Okay, so I think this is a good time to stop for me, and let's do 10 minutes break, and then I'll start talking about the transition. There is an approximation one can do for large scale. I don't want to do it now because it will take too much time, but that gives some an approximation to the transition point, which is useful. Okay, 10 minutes. We start at 4:20.
Quello che fate voi nel lecture, cioè voi.
Okay, so transition. So the first so what are indicators of the transition? So on the localized side, we say that the variance of the imaginary part of the propagator this goes to infinity, okay? And here instead it goes to 0. The level statistics is Poisson, and here is GOE. Okay? The participation ratios, for example, P2, okay? Here are there. Here, sorry, 1. Here the 1 will be. Very good. In modern times, this is indicated by the R parameter. And we found with Piotr and collaborators that among the various participation ratios is actually good to take the entropy, the fractal entropy of a wave function, okay, and then check how this changes with the system size. Okay, so this D will be 0 at the transition, 0 in the localized phase, and 1 in the delocalized phase. R is usually 0.53, 0.38. You can normalize it to be 1 here and 0 here. Okay. So what happens? I take my, and we usually call this phi, if it's normalized, phi is R minus R Poisson minus divided by R Wigner-Dyson minus R Poisson, okay? Good. Oh, R is the R parameter that has been also mentioned today by Marcos, the Organization use. Lessian use parameter. Okay, so I have 2 points in my parameter space, phi, d, or whatever. This is the localized point phase, and this is the ergodic phase. Then I need to discuss how, when I increase the system size, my numerics flows. Okay, and typically, if there is no transition, for example, if I do the Anderson model in 2D or in 1 dimension, okay, then I start with small system sizes that my phi or d can be even large, okay, quite close to 1. And then I increase my system size, and my flow just goes here. Okay. For example, this is what happens in d equal 1 and 2. In d equal 3,
This is a fixed disorder, right? You are, this
yes, you fix this. The disorder tells me the initial point, essentially. Okay, I start here, I start with a certain disorder W and a certain initial point L, and then I flow. If I start with larger disorder, I typically start closer here, but then I flow. Okay? Instead, if I have a transition, the flow changes depending on the value of the disorder that I have at the initial system size. Okay, good. Now, the way to understand finite size scaling in model physics is through the renormalization group. Okay, the renormalization group is a technique invented by Wilson and Kadanoff, Meadows, but made on proper standing. Everybody uses it. There is a before Wilson and after Wilson. Okay, that tells us what happens when I cost grain my system. Okay, so how do I connect this with finite size scaling? Chapter 5 of Cardy's book. Okay, so which is on my bedstand, by the way. And my coffee on my bedstand. I'm going to go and check. Okay, so this is the following. And what you do is you check how you compute how your system changes, how the Hamiltonian parameters change when you increase, you coarse grain your system. Your system had a certain lattice size A, okay, and then you send the lattice size into BA, and then all the parameters of the systems, W, if you have a temperature, if you have a magnetic field, they change. Some parameters were 0 and then they are born. Okay, some were large, become a little bit smaller. Some were small, become a bit large. Okay, so the inverse volume of my system, the number of blocks that I have, then V is the number of blocks that I have. V minus 1 is one of the number of blocks that I have, actually increases. It's a relevant parameter, okay? So my volume measured in the original and after the transformation, okay, v to the minus 1 is a relevant parameter, okay? So every function that I have, phi of w, okay? Now, by w, let me take the normalized disorder, for example, if there is a W critical, was just the disorder. Okay. One, this will change, okay? Under the normalization group, if I change my W prime in some way, which I don't know, I'm not telling you how this changes, okay? Okay. If I change W prime and V minus 1 like this, I'm still describing the same system. I haven't done anything different. Okay, I'm just changing, coarse graining the thing, but keeping everything. Okay, and therefore this doesn't change. Okay, so to connect the finite size scaling to the normalization group, which is the evolution of these parameters under coarse graining B, it's enough to notice that if I do this enough times, such that my final B is such that B to the D times V minus 1 is equal to 1, then my volume disappears. Okay? So, the dependence on the volume is contained just in the evolution of these things here. So I need to do enough scaling to get to the point in which I scale to the entire volume, and then I stop there. And then I have to look at what are the parameters, what are the... Okay? Good. So this is a very... So... Students, how many of you have taken a class which involved randomization group? Only 1.5. Okay, so this is a problem because I'm not gonna say anything more than this, except that, okay, the whole thing about the randomization group is that you want beta functions. Beta functions tell you how some objects scale with when you change the scaling. Okay? So these things can be computed in field theories. If you have a field theory, you can compute this in some approximation, typically. Okay? Sometimes you even can do really well. And this thing here gives you the entire critical theory. Now, I just told you that you can trade this B with V. Okay? B to the D with V. These are logarithms, so they're just a... Okay. So, for example, if I study now D log phi by D log V, I will get the beta function that if I had the field theory, I could compute. The great thing about 2025 is that I can do this numerically without even knowing what field theory I'm talking about. Okay? So I can study the beta function for these variables, phi, these observables, okay, by just doing numerics at different system sizes. putting all the data together, taking derivatives, and obtaining curves. With Piotr, we had a lot of fun, and with my student Carlo too, also separately, and also with Lev, who just left, to study even many body systems, like the quantum sum model, and reconstruct the beta functions for them. Okay? But first, let's constrain this beta function for the Anderson model. Now, the issue is the following, okay? So what really matters here is that this function phi of W is an analytic function of W. What's non-analytic is the behavior of the W and all its friends, temperature, external magnetic field, on the normalization group. Okay, so the things that are going to appear here are essentially, these are going to tell you about the scaling dimensions of these operators here. These are the things that scale. Phi and D are observables, they are all analytic functions. Okay, good. Now, having established that taking the derivative with respect to B, with respect to V is the same thing, let's go to the gang of four. Okay? Abrams, Anderson, Ricciardello, Ramakrishnan. After Wilson, they don't cite Wilson. Yes, they.
At that time, they are genius.
No, it was a year after. No. So the story is actually more interesting, and it's explained in an interview that Anderson gave to Shivaji. Yes, exactly.
And he didn't.
I didn't cite it. I never cites Wilson ever in any paper. So Phil was really convinced that he actually had arrived at the same ideas in the long range chain, the one that then led Kosterlitz and Taulest. So go and listen to that interview, it's fantastic. Okay, very good. So, okay, good. So the idea is the following. There is the object, okay, my conductor, okay, or insulator, size L, and I double it, okay? So first of all, I want to describe this thing. I need to describe this thing in terms of something, okay? If it's a good conductor, then I can describe it in terms of the conductance and the conductivity first, okay? So the conductivity, by the way, the conductivity, in the first lecture, I gave you, one of the first things actually, I gave you Einstein's relation relating the conductivity and the diffusion coefficient, but I didn't tell you, okay? I just told you that, that we were taking a limit in which we were just getting rid of the diffusion coefficient, okay? And fixing this ratio with the mobility, and this ratio which gave the diffusion coefficient. If you remember, okay? Now, this can be also written as d divided by kBt is equal to mu. Okay? And this is Einstein's relation, because the mobility times the charge times the density is the conductivity. Okay? So that's a neat way of finding Einstein's relation without ever referring to anything, essentially. Okay, so the conductance is, this is the conductivity, which is proportional to the diffusion coefficient. So the thing that I expect in my system when I change the system size, okay, is that the conductivity, the diffusion coefficient should be fixed. In fact, we also computed in the first lecture, we computed the diffusion coefficient without ever telling what was the system size. We assumed it was infinity. Okay, so this is a constant. The conduct, but in order to make all these discussions, I need something which is dimensionless. Okay, so dimensionless is dimensionless conductance G, which is conductivity times L to the D minus 2 divided by the quantum of conductance G0, which is E squared divided by 2h bar. 2h actually, not, sorry, 2 E squared divided by h. Okay, good. So, very good. Now let's compute the beta function. Let me compute it. Let me compute like d log g divided by d log d log L. Okay, then we'll see that we divide by d. And this gives me, since this is independent of L, if it's a good conductor, so if the dimensionless conductance is much larger than 1, then this is d minus 2. Instead, if it's a bad conductor, if we are in an insulating phase, then G, like everything else, should depend on the localization length exponentially. Okay? And if you compute this, you find d log G divided by d log L is equal to log G. Okay? Good. So, if I plot as a function of log G this beta, I see two distinct cases. Either D is larger or equal than 3, and then I have this is positive here, and then this is independent of the number of dimensions, so and it becomes negative. D is less or equal than 2, okay? Actually, it says strictly less than 2, and then this thing is negative and stays negative everywhere. And this simple argument explains why in 1 and 2 dimensions, you cannot have a transition. The beta function is always positive or negative. Okay? If it's always negative, then the flow is in this direction. Very good. Okay. Now, let's go back to our modern tanks. And let's see if we can okay. Maybe I need more space. Now, what do you expect? Well, for phi or d, okay? So let's say for d. If I am close to the localized phase, to the delocalized phase, I have a very good conductor, okay? Then D should be more or less be equal to 1, and the corrections should be analytic in G, okay? So, there 1 over G. Let me write 1 over G. Now D, yes, sorry, it's not the diffusion coefficient, is the fractal dimension. Thank you. G is this. G is this dimensionless conductance. Okay? Okay. Phi also will be something like 1 minus 1 over g. I mean, the coefficient on top are not important because I'll be taking logarithm derivatives and so on and so forth. Okay, again, close to the, for a bed conductor, for a double insulator, it will be something like this. And also this will be something like this. So beta, so here, let's say d phi, d log phi. No, I have to write at place. D log phi by d log v, okay? Since this term here goes like L to the d minus 2, okay? I leave you to prove that in this case, beta becomes d minus 2 divided by d, 1 minus phi divided by phi, or the same thing, d minus 2 divided by d, 1 minus d divided by d. Okay. Actually, I'm going to be using this more because the numerics is better for this thing here.
Is phi.
Okay, so phi is this. D was derivative of the entropy divided by the log of the volume.
R minus. Wait a second, I lost.
Okay, so R is the R parameter of user Ganesyan and defines whether you are in GOE and you want to normalize it to be between 0 and 1. So you subtract RT and divide by the distance.
But now you are writing an equation on net. Phi with d.
No.
No.
Now I'm looking at phi and say close to the critical point. Actually, let me talk about phi. Let me talk about d. Okay. Let's talk about d. Okay. Close to the critical point. Okay. D is 1 minus 1 over g. Okay. If this is true, the beta function, like there it was d minus 2. Because of the way d is written, the same argument tell me that it's d minus 2 divided by d, 1 minus d. Okay? So let's write down this thing. This is the ergodic fixed point, okay? And I enter the ergodic fixed point with the slope, which is d minus 2 divided by d. Okay? Because of this. Very good.
So phi now we don't talk because I
But forget, there is a universal function phi of d. If I tell you d, I know what phi is. Okay? Let's focus on one thing. Okay. Again, in the localized phase, this is 1 over d log d. Okay, so it's negative. So if d is larger than 2, the slope is positive, and here is negative. Exactly for the same argument there must be a transition in between. Okay, there is a crossing point. All the points to the right will flow to the ergodic fixed point. All the points to the left will flow to the localized fixed point. If d is equal to 2, and lower, this thing will always be negative. Okay, so you will always flow to the localized fixed point.
am I right that here I'm already working in the assumption that this is a one parameter scaling?
Yes,
Okay.
yes, that was the whole.
Starting from 1 minus 1 over g, there you're putting the assumption that there is the only parameter is g.
Yes,
Okay.
there is one parameter, is g. One parameter scaling means that beta is only a function of b.
Yeah.
Okay? It's not separately a function of D and L. Okay? And this is true for essentially every observable. G, D, phi, so on and so forth. And there is a dictionary, a function that translates phi into D, into G, and so on and so forth.
So when you numerically you compute these quantities and you show the plots, you are already working under this assumption.
No.
No,
When we compute the
because you are doing the numerical derivative, and so you.
yes.
Okay.
So if the curves fall on top of each other, then I am in one parameter space. Now, good. So, I think, which I don't know where did I put. Did I put it here? Did I put it here? I think I put it here. Take the limit b to infinity. We have already seen that for the density of state, in that case, we get the dome, right? The semicircle. D goes to infinity means that this slope becomes 1. Okay? And so we have that D as corrections 1 minus, okay, 1 over n, over V. And these are random matrix corrections. Okay? This we know that the corrections that we get in a random matrix V by V of the fractal dimension D, okay, they are 1 over V. So D-dimensional Anderson model, it's not in the scaling regime of random matrix, not even in fully developed chaos, unless I take D goes to infinity. The corrections know that you are at finite dimension. Okay? And they have this D minus 2. So the point is random matrix theory. The flow is not random matrix theory. It has a different slope. And the slope is because this is an Anderson model and test structure. It's not a structureless object. So when we say this is random matrix theory,
This is the capture this D minus 2 divided by D, like banded or checking.
this is a question maybe for Ivan. Do you know by random matrices which are scaling with different powers? For example, close to the correction, they don't go like 1 over V, but go to different power? Maybe not. No, I don't know. I don't think so. Okay, so yeah, so this is important because the slope is important. This is also the center of the discussion in a paper we just published with Lev on the quantum sun model. Because this is now a problem. The slope with which you go to the fixed point is important. That makes the universality class, the slope, not the point. Okay? So beware when you talk about random matrices, everything is random matrix and without checking these kind of things. Okay. It's important. Okay, and then
Does this slope depend always in the dimension, as you said, E minus 2 over D?
yeah,
Only on.
yes,
So everything goes like this, but.
yes, and you can check. You did with Piotr with different dimensions. You check the slope. It's D minus 2 divided by D, and the physics is that the diffusion coefficient is the constant. So the Anderson model on the lattice develops a diffusion coefficient which depends. It becomes independent of the system size. Since that is the quantity independent of the system size, everything else has this dependence d over d minus 2 divided by d. Okay.
But you like to calculate the contact because there is one
Mhm.
in the higher dimension above 2, you would like to still calculate conductance, right? Not conductivity. But they will be different by the dimension.
Yeah.
Sorry, yeah. So this,
Yes.
otherwise you
Yeah.
lead and
Yeah, it's here. Because this will be proportional to the diffusion coefficient will be constant, and this will acquire this dependence. And this is every quantity, like the spectral ratio, the fractionality will depend on this quantity, not on this quantity. Okay, they have to depend. It's dimensionless quantities that you have to look at, and it's not.
By the way, that is the regime that is easy to do numerically, right?
Yeah.
Okay.
Yes. Yes. Okay, very good. What do we have? Then we have from this simple thing we can derive this simple thing here. We can derive a lot of very interesting things. I give you a couple, and then I think I'll stop and.
D equal to 0 or close to 0, it will also should take another name d, small d to infinity, right? And beta is 1 over d log capital D.
Yes, I don't want to talk about that at the moment because that's the second part. Because when I take d that goes to infinity, here you are right. This thing, two things happen. This point flows here, and this line disappears. So, but that's something I want to do later. That's and then you are left with two parameter scaling. Okay, this is one parameter scaling so far and works fine. So the one thing you want to say. So suppose you are at d equal 2 plus epsilon. Okay, then I just have a little bump here, right? Okay, and therefore and then I can approximate beta as minus d minus 2 divided by d 1 minus d, okay, minus square, something squared, okay? So let me work close to d equal 1, okay? The only thing I know is that the derivative at d equal 1 has to be d minus 2 divided by d, okay? I think this is positive because there is a minus here, okay? And then there is a quadratic part that goes down, okay? Good. Now, the initial point is close to my d equal 1. So I can study what's the critical point there, right? How do I study what's the critical point? Well, I have to solve beta equals 0. Okay? At beta equals 0, I have two solutions. One is d equal 1, the other is d critical is 1 minus epsilon divided by 2. Okay? And the derivative at the critical point, these are all quadratic things, you can do it. Clearly, by symmetry is epsilon divided by 2. Now, if you look at the equation d log d divided by d log v is equal to, how do we call this, alpha, okay, some slope d minus d critical, close to the 0, okay? Then for you as an exercise, okay, if you are older, you have done this multiple times, the solution of this equation is that d is equal to dc plus L over psi to the 1 over mu, where psi is your initial D0, okay, minus dc to the minus nu, okay. The way I wrote this thing is 1 divided by the coefficient alpha, okay, the dimension d, and the value of the critical point dc. If you put these things all together, this is 1 over epsilon. Okay? So this is the result of the epsilon expansion around 2 dimensions for the Anderson transition critical exponents. You can obtain exactly the same argument if you compute one loop corrections in the supersymmetric sigma model. But here it's just it's automatic. It comes from this. Okay. And this is great because you get to 1 over epsilon, right? So first of all, you notice that it diverges when epsilon goes to 0. Okay. And then if you put epsilon equal 1, you get that mu is equal to 1. Okay. Which is wrong. Because we know that at epsilon equal 1 in 3 dimensions, the critical exponent is 1.52. Okay. Unfortunately, things become even worse. If you use the nonlinear sigma model to compute epsilon expansion, you go to 5th order. Ikami did that. You find, first of all, that this is non-zero, then so the 1 loop is non-zero, the 2 loop is 0, the 3 loop is 0, the 4 loop is 0, the 5 loop is non-zero, which makes you suspect that maybe somebody should check the 5 loop calculation of Ikami. That somebody is not me. Okay. So that's really something. But Edouard Brezen told me once that he had checked it. So
They are in the same group, so they support each other. We should
I know, but I trust Edouard. I don't know, but and things become worse. If you add the 5 loop order, they become much worse. If you put epsilon equal 1, you get a critical exponent which is like 7. Okay. If you try to do some other not other, what's called resummation. But resummation. So it's done. You can get something, okay. But it works for 3 dimensions, doesn't work for 4 dimensions. Okay. So nobody knows how to compute the critical exponents in the Anderson model in 3 dimensions. Full stop. This is I hope somebody could soon
I'm sure it's a triviality. We said that in D equal to infinity, we get a correction that is the same of random matrix theory.
yes.
So I would expect that sigma model should work this better and better, more closer I am to the random matrix case. So why instead work well for D equal to 2 plus epsilon?
Because the sigma model, in the random matrix case, you can take this approximation which you make you take many channels, okay, and that you're not destroying localization doing that because you're already delocalized, and then calculations simplify.
So let's say putting things differently, do we understand why the sigma model works well for 2 plus epsilon with epsilon small?
Oh, in fact, it doesn't work well. The sigma model does not work for 2 plus epsilon.
Not even for, I
No.
was working well for epsilon sufficiently small, much smaller than 1. Instead, no.
I mean, the 1 loop, yes, does, but it's not clear if that series has any meaning, actually, is even. Okay, so my is the following. You are expanding around point at which there is no transition.
Which is not a good idea.
It's not a good idea.
Okay.
Okay, it's not like expanding around 4 dimensions. In 4 dimensions, the easing model has a transition, perfectly fine. What changes are the critical exponents if you change epsilon? Fine. Okay, there is an upper critical
By
exponent.
definition, in non-analytical chain.
Exactly.
Okay.
It's like expanding,
No, it's clear.
Uh,
Okay. Okay.
so it's not, you are generating the transition with the expansion itself. There is no transition before. If I go to epsilon negative, there is no transition. Not that there is a transition d larger than 1. There is no transition, full stop.
One would be tempted to guess that if you break time reversal invariance, then in equal to 2, you have the transition, so maybe 2 plus epsilon is under good control.
In the symplectic ensemble, yes.
So the GUE, no? The GUE is already breaking the time reversal invariance. So
No.
No, it's just spin orbit.
In orbit does that. GOE doesn't. This is GOE.
no, this is GOE.
Yeah.
But I was thinking GUE should be already good in principle, no? Because anyway,
No,
I think
yeah.
2 plus epsilon is well behaved
I don't know actually. No.
because that's the transition you have. So
Yeah, but the transition is already somewhere around here, and with the spin orbit coupling, right? It's you're mixing two things. It's okay. So good. Exercise for you, and then I will stop because clearly I will talk about the 2-parameter scaling here. If you are at epsilon equals 0, okay, this is the beta function. Minus 1 minus d squared. Okay, solve the equation d log d by d log v is equal to minus 1 minus d squared. Okay, and this tells you what's the flow on this line here. It's an extremely slow flow. Okay, but if you do appropriately, you will find that the data indeed falls on this thing. I will stop here, and tomorrow I will continue from here, 2-parameter scaling, and then I will do this thing here.
thanks.
Thank you very much.
Cioè, un approccio perché il Sigma Model di fatto è random matrix theory.
Sì.
Di fatto. Quindi direi che fa schifo per tutti i di finiti, a meno che non vada ad infiniti, perché è l'unico dove c'ho le correzioni tipo random matrix theory, direi. No? Se vuoi messa a dire
Cioè,
effettivamente.
il random matrix theory non ha una transizione.
No, infatti. Non ha una transizione dall'altro lato, cioè è sempre dilocalizzato.
Sì, cioè c'ha una beta function che è una retta.
Esatto. Quindi, ma perché a qualcuno gli è venuto in mente di usare